Hey, welcome to The Explainer. Today, we're going to break down one of the most fundamental ideas in all of medicine. It's a really elegant concept that explains how thousands of different drugs work, and it's all based on a simple analogy you already know, a lock and a key. So, have you ever really stopped to think about it? You take a tiny pill for a headache, and somehow it knows exactly where to go to target the pain. How does it know not to, go work on your big toe instead? Well, the answer isn't magic. It's all about something called molecular specificity. And really, the best way to wrap your head around that idea is with that simple but incredibly powerful analogy that is the bedrock of modern pharmacology, a lock and a key. The drug is the key, and a very specific part of your cell is the lock. So, in the world of science, these cellular locks are called receptors. You can think of them as these tiny, complex protein machines sitting on our cells, and each one is designed for a very specific job. They just wait for the right molecular key to come along, and when it binds, that machine switches on and triggers some kind of action. This is the core mechanism for most medicines out there. Okay, so if drugs are keys, it turns out not all keys are created equal. Let's start with the most straightforward type, the keys that are designed to work perfectly. These are called agonists. So an agonist is basically the correct key for a lock. Imagine it sliding right in, turning smoothly, and click, the lock opens. In our bodies, that opening is the cellular response that the drug was designed to create. Simple as that. So to put it a bit more formally, an agonist is just a chemical that activates a receptor and makes something happen. And what's so cool is that they often work by mimicking the body's own natural keys, things like hormones or neurotransmitters, to produce an effect we want, like maybe reducing inflammation or opening up your airways. Okay, but here's where things get really interesting. Just because a key works doesn't mean it has the same effect. Some are like master keys that throw the deadbolt wide open, while others, well, they might just jiggle the latch a little bit. This brings us to two main kinds of agonists. First, you have a full agonist. That's your master key. It produces the absolute maximum response you can get from that receptor, 100%. But then, you have a partial agonist. Now, this one's a bit tricky. It fits, it turns the lock, but only part way, so it gives you a much weaker response. Now, we've got to talk more about this partial agonist, because its function is so unique and, honestly, it's an incredibly clever tool in medicine. It's not just a weak key. It actually has this fascinating dual personality once it's inside your body. So here's how that split personality works. First, the partial agonist creates a little bit of a response all on its own. But second, and this is the crucial part, while it's sitting there in the lock, it's physically in the way. It blocks the body's own super powerful full agonist from getting in. So it activates a little, but it also blocks a lot. It creates this ceiling on the total effect, which is perfect for treatments that need a more balanced, moderate response. All right, we've covered the keys that work, but what about the keys that are designed specifically not to work? These are the blockers, and they're called antagonists. This is the whole idea behind an antagonist. Imagine a key that's cut just right to slide into the keyhole. It fits in there perfectly, but all the teeth are wrong. You can't turn it. It just sits there. And as long as it's stuck in there, no other key, not even the right one, can get in. So the real power of an antagonist isn't what it does, but what it stops from happening. By just acting as a placeholder, it blocks the body's natural on signals from doing their job. Think about beta blockers for high blood pressure. They work by blocking adrenaline from hitting receptors in the heart, which keeps it from getting overworked. And this chart just lays it out perfectly. Look, they both bind to the receptor, right? They both fit in the lock. But look at that next line. Activates receptor? For the agonist, it's a clear yes. For the antagonist, it's a big no. That simple difference is the foundation for thousands of different medicines. And just like agonists, antagonists have their own variations. A competitive antagonist is kind of like it's in a tug of war. It binds, but it can be kicked out if enough of the right keys, the agonists, show up. But an irreversible antagonist, man, that's like breaking the key off inside the lock. It binds so strongly, sometimes permanently, that it doesn't matter how many of the correct keys you have, they can't get it out. Okay, let's look at one last type of key. And this one is, well, it's kind of mind-bending, and it turns our whole simple analogy on its head a little bit. Get ready for a pretty wild idea. You see, it turns out some of our cellular locks aren't just sitting there completely off. They have this low, constant hum of activity, a sort of idle mode. So what if a key could fit turn the lock, but instead of opening it, it actually double locks it, shutting down even that background hum? And that is an inverse agonist. It doesn't just block the keyhole like an antagonist does. It actively grabs the lock and turns the key in the opposite direction, forcing the receptor into a totally inactive state and silencing even that baseline activity. Okay, so agonists, antagonists, inverse agonists. We've got keys that turn things on, keys that block things, and keys that turn things off completely. Why does understanding all this matter so much for our health? Because this right here, this is the very foundation of modern medicine. It's called rational drug therapy for a reason. Scientists don't just randomly stumble upon drugs anymore. They identify a biological lock that's involved in a disease, and then they painstakingly design the perfect key, whether it's an agonist or an antagonist, to interact with that lock in a super precise way to treat the condition. This quote really says it all, doesn't it? The whole point of digging into these intricate lock and key mechanisms is to move past guesswork and build a rock-solid scientific framework for creating treatments that are both effective and safe. And that leaves us with this incredible thought to chew on. Our bodies are just filled with these molecular locks, and we're discovering new ones all the time. For every single one we find, there's a chance to design a brand new key, a new medicine that could potentially treat diseases we currently have no answer for. The search is definitely far from over.